So this is a real quick video tonight to show you how to draw Lewis structures for things with expanded octets. Remember, an expanded octet occurs when you have an element that's in the third period or greater on the periodic table, implying that it's got electrons in D and F sublevels, and as a result of the extra number of electrons, it's possible that a central atom could have more than 8 electrons on it. So I've got 4 examples tonight that I want to go over with you. We will use the TVS model, the total electrons, valence electrons, shared electrons model to figure out what's going on, and then we will draw those Lewis structures. So the first example I have is PF5. Okay, so immediately with PF5 we can see that there's definitely got to be more going on with that. So when we assign total electrons, valence electrons, and shared electrons to PF5, we can see that phosphorus will want to have 8 electrons, and we know fluorine will each want to have 8 as well. So 5 times 8 is 40. Plus 8 more for the phosphorus is 48 total electrons that want to be accounted for. In terms of valence electrons, we know that fluorine in group 7 of the periodic table will have 7 valence electrons, so 7 times 5 is 35, plus phosphorus being in group 5 is 5 more is 40. So 48 minus 40 gives us 8 shared electrons. Now, we can see very clearly that there's no way we can arrange a phosphorus with only 8 shared electrons, which would be 4 bonds if you got 5 things attached to it. So the only way we can do that is if we expand the octet. To share the number of electrons we need, to change the number of electrons would be 10, so 10 shared electrons. And the only way you'll get from 48 total electrons to 40 to get 10 is if you change the 48 to 50. So we want to account for 50 electrons. Now we can see that we can arrange the fluorines around this, which we could have done before, knowing what was going on, and we want to place 30 valence electrons around everything else. So we start at the outside atoms, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 20, 22, 23, 24, 25, 26, 27, 28, 29, 30. So we've placed all 30 valence electrons. Now, just to get an appreciation of what's going on with the VSEPR structure, we can see that there are 5 areas of electron domain density, 1, 2, 3, 4, 5. All of them are bonding, so that's going to tell us that we're going to be trigonal bipyramidal, both for electronic domain geometry and for molecular geometry. So the next example I wanted to look at is going to be SF4. Okay, this is a little bit more tricky because when we look at it, we can see that it's possible that there will be 4 fluorines arranged around the central sulfur. So let's go ahead and confirm. So total electrons, again, sulfur will want 8, fluorine will want 8 as well. So you've got 4 times 8 is 32, plus 8 more is 40 total electrons that want to be accounted for. For valence electrons, you got 4 fluorine, so 4 times 7, being in group 7, is 28, plus another 6 for the sulfur will be 34, and we can immediately see the problem is that there only wants to be 6 shared electrons. So when we arrange that around your sulfur, we can see that it's got to be 8. So we have to increase this to 8. In order to increase that to 8, we have to increase this to 42. So 42 electrons total have to be accounted for. Now we can place the fluorines around it. 1, 2, 3, 4. And now we want to take the difference between 34 and 8 in order to figure out the number of valence electrons that we have left to place. So that's 26. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, starting with the outside. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We want it to place 26, so where do the remaining go? They go in the central atom, the expanded octet. So when we take a look at this, now we can see that there are 4 areas of electron density that are bonding areas and 1 that is a non-bonding area for a total of 5 areas. So the electron domain geometry will be, again, trigonal bipyramidal, but the molecular geometry is going to be different. We have 4 areas of bonding density, 1 non-bonding area, and so that's going to be seesaw shaped. And you can refer to your book for the reasons why. Next example I wanted to go over is actually a polyatomic ion. It's I3 minus, and the name of this ion, I'm sorry I have to go look at my reference book here because I totally forget, it's not one we see very often. Triiodide ion, makes sense. So now we're going to look at TVS for the triiodide ion. First of all, we can anticipate it's going to have an expanded octet because iodine very low in the periodic table, certainly beyond the third energy level. Total electrons, there are 3, 8 in each, this would be 24. The valence electrons, we know that there are going to be 3 times 7, iodine being in group 7 is 21. But don't forget we have that extra valence electron right there. Plus 1 equals 22. So 24 minus 22 is going to equal 2 shared electrons. Well, obviously I with an I to another I has got to be 4 shared electrons. So we need to increase that to 4, increase that to 26. Okay, so now what we need to do is we need to place 18 more electrons around this particular ion here. So we'll start with the outside. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, so we can see that now there's 18 electrons that have been placed, 6 lone electrons around each element, and because of that, it's going to be a 1 minus charge. Now, when we look at this thing, we can see that there are going to be 1, 2, 3, 4, 5 areas of electron domain density around that central atom. So again, the electronic geometry will be trigonal bipyramidal. This just happens to be coincidence. And then the molecular geometry, in this case, is going to be linear. Okay, so that's a kind of interesting situation right there. Okay, the last example I wanted to go over is going to be xenon. Let me try that again, a little messy. Xenon tetrafluoride. So again, we have a situation where we could think we could have just those 4 bonds. Okay, TVS to figure out what's going on there. 1 xenon and 4 fluorines for a total of 5 atoms. 5 times 8 is going to be 40 total electrons we want to account for. Our valence electrons, it's going to be 4 times 7, which is 28, plus 8 more is 36. So we can see that the difference is 4 shared electrons. Well, obviously, xenon with 4 fluorines bonded to it has to have more than 4 shared electrons. It's got to have 8. So we need to increase that to 8, and we need to increase this to 44. This one's a little different because we had to increase it by a lot more. Now the difference between 36 and 8 is 28. So we'll go ahead and place our fluorines around it. And we can place 28 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. Let's try that again. 25, 26, 27, 28. Okay, always placing around the outside outside elements first, and then going to the center. Okay, now we can see that the electronic geometry is going to be octahedral. There are 1, 2, 3, 4, 5, 6 areas of electron domain density, and the molecular geometry is going to be got that wrong. Square planar. That's how they are going to reflect from each other most. Okay, so hopefully this this helped you to figure out exactly what's going on here. Hopefully it gave an appreciation on how to do expanded octet electron configurations. Thank you very much, and have a great night.